And I noticed that YouTube has been having some errors or issues today. Let me make sure that the stream is actually working. Uh, and I think it is, right, it says live. As far as I can tell, it's working out. Let me just check one more thing to. It's like it's working. So what I'll do is go through some one in section 2. I may go through some additional problems as well. And what I'll do is move back to section 1.1 and kind of go sort of rapid fire. So let's see what we have here. We'll go through 1.4. It's actually, yeah, I'll just go rapid fire through the list I have here. And some people may join me later, so I may repeat a problem later or something like that. But I plan on being here for at least 8 hours, something like that. I may take a break to get something to eat, and then come back. And I don't think the stream will continue that for that whole time. I might pause the stream for a while, and then come back later and keep it rocking. So here we go. I'll start with section 1.2 in the book, and I'll go to number 10. And actually, let's go ahead and start with 1.3 since there's some 1.2 problems already. We'll go to 1.3 and number 6. And I probably should adjust the stream name, but I could do that later. I'll adjust it to 1.1 to 1.4. So we'll make this 1.4. And we'll start with number 6. Make sure this is the right section. 3, number 6. There we go. I have it highlighted. So I'll just write the problem out and make the stream a lot larger here. And if anyone's interested in tutoring, I have that available. I'll make sure that's showing over there. There we go. All right, so 1.4, number 6. It says give the general solution to the equation x1 plus 5x2 minus 2x3 equals 0 in R3 as a linear combination of two vectors as in the text. As a linear combination of two vectors, which we're familiar with. So let's see how we'll start this. I'm reminded to solve for something. So we can say x1 equals 2x3 minus 5x2. So we can say x1 equals, so we can say the vector x equals x1, x2, x3, which equals 2x 3 minus 5 x2, x2, x3. So that equals, if I was to break these apart, there's no x1, so it'll be x2 and negative 5, 1, 0 plus x3, 2, 1, 0, 1, and that equals 0. So we can say x equals x2, negative 5, 1, 0 plus x3, 2, 0, 1. So that seems to be what they're saying. Give a solution to this equation as a linear combination of two vectors. So that seems to be that. Um, then we have find the specific solution of the equation x1 plus 5x2 minus 2x3 equals 3 in R3, give the general solution. So really, what this will end up being is the same solution. So this is A. It should be the same solution, but we have 3, 0, 0 plus x2, negative 5, 1, 0 plus x3, 2, 0, 1. And x will equal that. So let's work through this and see if that's the case. So now they're giving us the equation x1 plus 5x2 minus 2x3 equals 3. And that is in R3. You see it's the same equation except there's a 3 on the other side. So I'll still solve for x1 equals 3 plus 2x3 minus 5x2. And similarly, I can put this into a vector form and say basically x1 is 3 plus 2x3 minus 5x2, x2, x3 for an x1, x2, x3 vector. So that's going to be 3, 0, 0 plus there's no x1. And then we have negative 5, 1, 0 for x2. And then we have 2, 0, 1 for x3. So that seems to be that. And then C says, give the general solution to the equation x1 plus 5x2 minus 2x3 plus x4 equals 0 in R4. So it'll be done the same way. I say x1 equals 2x3 minus x4 minus 5x2. And notice I usually put the one that's negative on this side first on the other side so I can start with a positive. That's something I learned from the math books and such. So that means that x equals x1, x2, x3, and x4. So that's going to be no x1, negative 5, 0, 0, 0, x2 plus, hold up, I missed the 1 here. There's still going to be an x1, x2 there. So it's going to be a 1. And then we have 2, 0, 1, 0 for x3. And then we have the last one, negative 1, 0, 0, 1, x4. And by the same token, the second part of C has the same equation, but except it equals 3. So that'll be the same thing, except it'll be equals 3, 0, 0, 0, plus the rest of that. So let's go ahead and take a look at the answer key and see if we got that correctly. So this is 1.3, number 6. And this looks to be correct. So we have 5, negative 5, 1, 0, x2, 2, 0, 1, x3. You can just add the 3 there. And for the next one is for B, the full thing except that. For C, negative 5, 1, 0, 2, 0, 1, 0, negative 1, 0, 0, 1. And the same thing except you add a 3 in there. So that's correct. So let's go to 8. We have it says the equation 2x1 minus 3x2 minus 6x3 equals negative 4. And it defines a plane in R3. Give its normal vector A. Now, the first time I did a problem like this exact problem actually, I did a very complicated thing that's unnecessary. So basically, the way it works is whenever you have any kind of plane or any kind of equation, whether it be a line, let's say if it was just this portion of it, then the normal vector would be 2, negative 3. But since it's three terms, all the terms on the left side with a constant on the right side, the normal vector, which I'll call n, is 2, negative 3, 6. So it's always going to be the coefficients because it's basically n1, x1 plus n2, x2 plus n3, x3 equals, let's say, c. So that's the normal vector right there. Find the distance from the origin to the plane by using projection. All right. So let's draw a coordinate system. Let's say we have a plane here. And the plane, let me offset it a bit so it's not, so let's say the plane is hovering there. And what we need to do is distance from the origin to the plane. So for one thing, we know that the distance from the origin to the plane, the shortest distance is going to be a straight line. So that means that this point, the line that meets at that point is going to be normal to the plane. So imagine that's still underneath the plane. And it's going to be normal to that plane. So for instance, if I also draw another line on top of this, and then make this dotted, I'll try drawing another line. So you can say the plane is underneath, the line is underneath that, and this makes a right angle underneath with the plane there. That's a right angle. So the shortest distance from the origin to the plane is going to be a right angle. So what that means is that the line, that vector is going to equal the n vector. So the n vector of the plane is going to equal that line. You just need to get the distance to it. Now, let's see the best approach here. Now it says by projection. So why don't we fill that out first? We have a point. We could find points of the line, but what we can say is right? So the plane is going to be made of two vectors. So we know we'll have a vector we can call u and a vector we can call v. And both of these will be normal to the plane. Excuse me, normal to the line. So we can say L dot u equals L dot v equals 0. And we could also say that I'm trying to remember the definition for projection. And we could also get XO. So why don't we do that? We're gonna find this point here, or some point on the plane that I'll call A. So let's go back to the equation for the plane we have, and I'll just copy it. So we can say we'll apply what we did earlier. We'll say 2x1 equals 6x3 plus 3x2 minus 4. So x1 equals 3x3 plus 3 over 2x2 minus 2. So now I can make this into two vectors. So x equals 3x3 plus 3 over 2 x2 minus 2 x2 x3, which equals, which is going to equal, I'm going to pull the negative 2 out. So negative 2, 0, 0, plus, there's no x1, plus 3 over 2, 1, 0 for x2, and plus 3, 0, 1 for x3. So now I know that my xo is this point equals negative 2, 0, 1. And we're going to call that A. So this point A is negative 2, 0, 1, even though that's a point on the plane. So what we can say is that the normal times u, the normal times v equals 0, Um, and now we have a u and a v. So this is going to be xo. This will be one of these planes here, u, and this will be v. So we have to solve that equation to get the components that we would need to make this thing work. So now we know that the normal vector dot u equals and I'll just do n1, n2, n3. Because in other words, the normal that we have here, and actually since I call that n, let's call this a. The normal that I have here is one particular normal on the plane, but we need one very specific normal that is coming directly from the origin. We don't know what that is exactly, but we know whatever that uh, vector is, we know that it's going to dot product to 0 with u and v. So we don't know what it is now. So I'll say a1, a2, a3, dot product. And we have the normal vector, excuse me, the u vector, 3 over 2, 1, 0 equals 3a1 over 2 plus a2, and that equals 0. So we have a2 equals negative 3 over 2 a1. And then we can say a dot v equals a1, a2, a3 dot, and v was 3, 0, 1. So that equals 3a1 plus a3, and that equals 0. So a3 equals negative 3a1. So now I could put all of a in single terms. So a equals a1, a2, a3, which equals a1, and a2 is negative 3 over 2 a1, and a3 is negative 3 a1. So that equals 1, negative 3 over 2, negative 3 a1. So that equals a. And a, we know, is going to be a real number. I'll write that the correct way. A1 is any set of real numbers. So I said solve by projection. I'm not convinced that we have to solve it by projection, but let's try to do it. Let me confirm that. So I need to be reminded of which one will be projected onto which one. Right? So we could look at it this way. Whatever this normal is, and apparently any number we pick for this, for A1, would allow that to work. We just need to find the specific A1 that comes from the origin. So what this means is that XO plus T A is going to be some point on the plane, and XO is 0. So that means TA is going to equal some point on the plane in order for this line to actually meet the plane. So that means that T A1 T negative 3 A1 over 2 and negative 3T A1 is some point on the plane. Why don't we pick a number that makes this easier? Since this should work for any number A, why don't we let A1 equals 2 since it'll get rid of that fraction? So this would mean that 2T and negative 3T and negative 6T equals the plane. And the plane, you know, equals negative 4. Actually, that's when it's put into the plane. So let's see what we can do here. All right. So XO is not necessarily uh, at the origin. XO is anywhere, like this point right here that we call it XO. So this means that since A is on the plane, that's where we get our projection from. So why don't I do this part right here so we can look at the plane while I'm working this part. And I'll move this over to give myself a bit more room. So what this means is that the projection of XO onto the normal vector is this. And drawing this here makes this a little confusing here. So remember that this is the line and that's normal. But also remember that every single vector is normal. If it's a right angle to that plane, they're all A. So you could even say that that's some scalar of A, let's say, like alpha A. So the projection of A onto the normal at the origin is the shortest distance. So what we want is the projection onto vector L of, let's say, XO. And this is XO, the vector XO. So we can say that XO dot A equals XO dot a vector that's perpendicular to, and actually let me the XO should be the one that's being uh bandied about. So why don't I make this notation a bit simpler? So XO is what's being projected. So we can say A is just what it is, that the XO that is perpendicular to A plus the XO that's parallel to A, because this X vector here can be broken up into two vectors that are right angles to each other with certain amounts of them in each. And we can say that that'll be A dot, and we can say that we can use the distributive property since it's a dot product to a sum. So remember yesterday I was mixing up the sum between the dot products, but if you have a dot product to a sum, you could distribute that dot product. So this is actually A dot product, the perpendicular XO plus A dot product, the parallel XO. And since any two things dot producted to each other that are right angles means zero, that's going to be zero. And we know that X dot product, the X component parallel to A, the projection onto that will be just as long as A. It'll just be a scalar, some scalar of A, whatever that scalar is. So we can say A dot some scalar of A. So so this is starting to work out. I forget exactly why we can't say a straight A. We have to say a scalar of A. But I do remember now that it would end up being X dot A divided by the magnitude of A squared equals alpha. And I'll make this in blue. Now, another thing we can do is we can say mm, X O dot A equals cosine theta magnitude of XO magnitude of A. Let me remind myself if that is the proper next projection. That is true, but that's not the proper one. So we want to go simply that the projection of X on to A equals some scalar of A. So whatever A is, there's some scalar of it that equals the projection of XO onto A. So then we can say that alpha equals projection onto A of XO divided by A. So now we can make these things equal to each other. And we have the projection onto A of XO equals XO dot A over A squared times A. And now we have the equation we need, and we know that the magnitude of that is going to be the magnitude of the distance, but I don't think they want the magnitude of the distance. They just want the actual distance. Find the distance. Well, the distance is going to be the magnitude. I was thinking they don't want the distance, they want the point, but they do want the distance, the magnitude. So now we have the equation we need, the projection. So the key to that is remembering that uh, this point that we have from the plane, the original plane equation, that's not necessarily where the normal uh, from the origin hits the plane. So now we can take the point on the plane that we have and project it onto the normal in the origin. And that's how we can get the distance from the origin. So now all we have to do is plug in. So XO we had as, we found it from the original equation. When we work that out, XO is negative 2, 0, 0. I don't know why I put a 1 there. And A equals, I chose 2 for A. That's why we have to put a scalar, because I chose 2 for A, but I could have chose 1,000 for A. Could have chose 1,000,000 for the A1 that gave us that value. So since I'm guessing or choosing a value to make this normal vector, it's not necessarily the exact length to hit the plane. It is just the exact length to go directly to the plane. And from the origin, it'll be the closest distance to the plane because it's normal, but it's not necessarily the exact length to hit the plane. We don't know that. So all we know is that since I chose 2 for A, all we know is that some scalar of this specific vector that comes from the origin and hits the plane. So this some scalar of A is going to equal, I believe I chose 2. I just didn't write it out, but A equals 2. So A equals 2, negative 3, negative 6. Right, so we'll just let that be A. That's our A. But we'll just say that the scalar that we're looking for is what's going to move that to touch the plane. So that's going to be our A. It's going to be 2, negative 3, negative 6. So I could either put the scalar on this and have to solve for the scalar there, or I could just plug that A in and consider the scalar part of the value inherently. And okay, so we can say X dot A equals 2, negative 3, negative 6 dot negative 2, 0, 0. So that equals negative 4. And we have the magnitude of A equals the square root of 2 squared, which is 4, plus 3 squared, which is 9, plus 6 squared, which is 36. So that equals 49. The square root of 49, that equals 7. So we have negative 4 over 7 times the magnitude of 8, and the bottom one is squared, by the way. So I believe I should be able to do these separately. Like I say, the magnitude of a squared equals 49. So I should be able to say magnitude of x o dot a over magnitude of a squared times the magnitude of a. So that should equal negative, well, the magnitude is going to be 4 over 49 times 7. So that equals 4 over 7. So that's the distance from the origin to the plane using projection. And I'm certain that is the correct answer. Let me check. Oh, yes, 4 over 7. So that is what we do to get that answer. All right. Now, we'll go to the next part. It says find the distance, find the point on the plane closest to the origin by using a parametric equation of the line through the origin with a direction vector 8. So this is easy enough. So basically, it just wants us to find that line L, which we drew out already. So L equals it's going through the origin. So we can say 0, 0 plus, we'll say beta A. So L equals beta A. Well, we can still keep it alpha A. So we have to multiply alpha by something such that it hits the plane. So let me think of how to do that. So we have an equation for the plane, which is this. Right? So we're saying that some scalar times 2, negative 3, negative 6 equals that. That's what it seems we're saying. And seems like I'm making this one more complicated than it needs to be. Let's see here. So we have the normal vector. We have the XO, which is the origin. Yeah, so they do have to equal. Whatever scalar we put on that vector, it has to equal something that we put in for that line. So I should be able to solve these separately. Why don't we try this? I'll say alpha 2 negative 3 6 minus 3 over 2 1 0 x2 minus 3 0 1 x3 equals negative 2 0 0. That should be a true statement. And now what we end up with is a nice matrix. 2 negative 3 6 negative 3 over 2 negative 1 0 3 0 1 alpha x2 x3 equals negative 2 0 0. So I should be able to solve this and get the answer. So let's see, negative 3 over 2. Oh, what was that? It was 3. Negative 3, negative 1 0 6 0 1. Negative 2 0 0. And let's see if we can solve for these three things. So I would say we could swap these things around. Why don't I first get rid of the bottom line? So row 2 plus row 2 plus row 3. I'm going to put that in row 3. So that's going to be 2, negative 3 over 2, 0, negative 2, negative 3, negative 1, 0, 0. And we have 2 times row 2, 0, 2 times row 2, negative 2, 1, 0. And now we can say 2 times row 1 to get rid of the fraction. 4, negative 3, 0, negative 4, negative 3, negative 1, 0, 0, 0, negative 2, 1, 0. And I'll do row 2 plus row 1 equals row 2. So then I would have 1, negative 4, 0, negative 4, 4, negative 3, 0, negative 4, 0, negative 2, 1, 0. Right? I'm going to subtract 4 of row 2 and make that my row 1. So what do we have? We have minus 4 is 0, plus 16, 13, 0, plus 8, 4, 1, negative 4, 0, negative 4, 0, negative 2, 1, 0. And I'm going to swap these rows. So that should become 1, -4, 0, -4, 0, 13, 0, 4, 0, -2, 1, 0. So what I'm going to do is I'm going to add 6 of row 3 plus row 2 is row 2. So 1, -4, 0, -4. 6 times -2 is -12, so that's 1. It's going to be 6, 4, 0, -2, 1, 0. And then I'm going to go 2 times row 2 plus row 3. And that's going to be my row 3. So that's going to be 1, -4, 0, -4, and 0, 1, 6, 4, and then 0, and 2 times that 0, 13, 2 times that is 8. All right, so let's see what we have. We have alpha, and actually let me divide this by 13. So it's going to be 1 and 8 over 13, just in case. And I can actually get rid of a few more things. Which one would be easier? But just in case, let's get rid of this 6 first. So row 2 minus 6, row 3 is row 2. So that's going to be, I'll copy all of this down first. Right, so that's going to be minus 6 row 3. So that's minus 6 and minus 36, 36, 48 minus 48 over 13. So that's going to make this 0, and that's going to make this minus, I'll just call it 4 minus 48 over 13. And what is going to be problematic? Let me, I'll use the calculator to find out what that is. 4 over 13. And one last thing, so it's going to be 4 row 2 plus row 1 to row 1. So going to be plus 4 and plus 16 over 13. So that's going to be 1, 0, 0, -4 plus 16 over 13. So that's -36 over 13. And 0, 1, 0, 4 over 13. And 0, 0, 1, 8 over 13. So as long as I didn't make a mistake on any matrix, this should be it. And alpha is going to equal 36 over 13 negative. What was the other variable? X2. X2 equals 4 over 13. And X3 equals 8 over 13. All right. So if I was to plug this in, let's see if this works. So we should be able to find out pretty readily if this configuration works. So we have 2 times negative 36 over 13. So that's negative 72 over 13. Negative 12 over 13. And did I add a negative there by mistake? Yeah, no, it's 3 negative 6. That's going to be positive then. And this is also going to be 6 times 36 equals 216 over 13. Let's see if this is equal. Negative 200 plus 6 over 26, 4 over 13, 0, plus 24 over 13, 0, and 8 over 13. So that equals negative 2 plus 6 over 26 plus 24 over 13. So that equals 1 over 13. That's not good. Oh, and 4 over 13 and 8 over 13. So perhaps it's a multiple. Maybe I missed adding something. Let's see what I might have missed adding. All right, take a look and see what I did last time. And we can try to work this out. Pretty sure this way will work, but probably just rushed on my matrix and did something incorrect. A simpler way would be to, so it is true that the line will equal the plane. So L equals P. And P equals negative 4. But not precisely. P equals negative 4. And L is some point on P. And L is going to be some scalar of alpha. And we know alpha is 2, negative 3, negative 6. And so that's going to be alpha 2, alpha negative 3, alpha negative 6. And these are the x vector components of a line that is on the plane. So this point is on the plane, and this point is an x, y, z on the plane. But inside the plane extends in all directions on that plane. So all I have to do is take my equation for the plane and plug these x values in and then solve. So the plane is 2x1 minus 3x2 minus 6x3, and that equals -4. So that's going to equal 2 alpha minus 3 -3 alpha minus 6 -6 alpha. But it seems kind of intuitive because you're kind of putting the same thing in that you've already put there. It is 4 alpha plus 9 alpha plus 36 alpha equals -4. So alpha 4 plus 9 plus 36 equals -4. So alpha 49 equals -4. So alpha equals -4 over 49. So I think I wrote my equation of the plane down incorrectly. Well, I see. So the point, or L, would be taking our alpha here, our line in terms of alpha, and plugging that in, and then we get the line which equals the point. So that equals -4 over 49 to -3, -6. So that equals -8 over 49, 12 over 49, 24 over 49. So this is the line or the point where from the origin it hits the plane. And if we take the magnitude of this equals the square root of each of these components squared, and summing them together, let's see what we get. Get in my calculator. They can put a plus in the wrong spot. Let's see here. My answer into a fraction, and it is 4 over 7. So that means that the that point works because the distance from the origin to the point is the same distance that we had when we got the distance parametrically. So this is our point, which is the line, which is on that plane, and we got it through the, we just have to remember to, I'm sure this will work. I probably will maybe go through later and see what mistake I made on my matrix. Must have made some kind of mistake on my matrix here. But an easier way would be to simply realize that the line is an x, y, z value, the line itself, including the alpha. So we can plug that x, y, and z into the plane and then solve that way. But let's take a look now, actually. Let's see what I did wrong with this matrix. Oh my gosh, I see what I did wrong. I left off my negative. So let's see what happens if I did this again and I didn't leave off my negative. So R2. So really this would be negative R2 and negative R2. Negative R2 and negative R2 plus R3. So R3. So negative R2 will make that a positive 6. And then this does equal 0. But negative R2 will make that a positive 2. So this would be a positive 2. And everything else would be the same. So then I had 2R1 is R1. So that stays the same. R2 plus R1 is R2. That stays the same. I have negative R4, negative 4R2 to R1. That stays the same. I swap those rows. Just have to remember to keep making this positive as we go down. Now 6R3 plus R2 equals R2. So now it'll be negative 6R3. So this would be minus 12 minus 6. So minus 12 still makes that 1. Minus 6 makes this negative 6, and that stays the same. And this is now positive. Then 2R2 plus R3. So now it's minus 2R2 plus R3 is R3. Minus 2. So that still will be 0 at the bottom there. Minus 2 will make that a positive 13. Maybe I should stop trying to fix it here because it's starting to get more complicated, trying to keep up with the negatives I'm changing. So, matter of fact, I'll just erase all of this. And after this problem, I'll take a break and come back. So now we have this. After swapping those lines, I will get 1, negative 4, 0, negative 4, 0, 13, 0, 4, 0, 2, 1, 0. And I'll have 2R3 plus R1, so R1. So that's going to be plus 2, plus 2. So that's going to be 1, 2R3. 1, 0, 2, negative 4, and 0, 13, 0, 4, 0, 2, 1, 0. And what's the easiest way to do this? I want to double the second row as well. 2R2, 2. I just don't want to deal with this odd number anymore. 26 and 8. So now we're going to have negative 13, row 3, to plus row 2 is row 2. So I still have to deal with the 13, 1, 0, 2, negative 4, 0, hold up, 0, 0, negative 13, 0, 0, 2, 1, 0. So I'm going to divide this by negative 13. I'm going to divide this by 2. So then I will get 1, 0, 2, negative 4. I'll get 0, 0, 1, 0. Then I'll get 0, 1, 1 half, 0. So I can move these around, and then I'll get 1, 0, 2, negative 4, 0, 1, 1 half, 0, and 0, 0, 1, 0. So I can say 1 half row 3 plus row 2 is row 2. And I can say negative 2 row 2 plus row 1 to row 1. So negative 2 row 3, I meant to say. Negative 2 row 3 plus row 1. So that's minus 2. Everything else stays the same. And 1 half, negative 1 half row 3 plus row 2 is row 2. So that's minus 1 half. So that's going to be 1, 0, 0, negative 4, 0, 1, 0, 0, and 0, 0, 1, 0. So alpha equals negative 4, x2 equals 0, and x3 equals 0. So let's see what happens here. So I made another mistake on the matrix. That means this process here probably is just not worth the effort. This is going to be negative 8, 12, 24, minus 0 minus 0 equals negative 2, 0. Nope. I probably just made another mistake on the matrix somewhere, so I'll skip this method. And just remember, if you're trying to find the parametric equation of a line from the origin to the plane, to consider the line a scalar of the normal vector coming from the origin to x or 0, so the line is just scalar normal vector. When you distribute the scalar, whatever it is, you actually have a point, an x, y, and z that you can plug in for the x, y, and z in the plane. And then when you plug that in for the x, y, and z in the plane, you can solve for alpha. And now you know the exact scalar to put on the alpha so it hits the line, because that scalar makes that point work in the plane. This means that point is hitting the line. That point on the line is hitting the plane. It's ending on the plane. So then you can just plug in that alpha into the scalar of the normal, and now you have the exact point where that line hits the plane. and the magnitude matches. So I'll be back. I'll take a break, get something to eat, and I'll update the title on this one, and we'll continue working some problems in section 1.1 through 1.4.